So today we are going to be continuing with the idea of polynomials, and we will be looking at them in both factored and standard form. We'll be graphing them. We'll also be writing equations to model them. Okay? So the two examples that were given first are in factored form. You can see that they're factored into binomials. If it is in factored form, you can use the zero product property to find the zeros. And I kind of introduced this idea yesterday. So remember, the zeros occur at the x-axis. So that would essentially be when y is equal to 0. So we did this with quadratics, where we would set each of them equal to 0. So now we're going to set all three of them equal to 0. So it'll be x plus 1 equals 0, x minus 1 equals 0, and x plus 3 equals 0. Now most of you know it ends up just being the opposite. So like usually you won't show this work after this example. But remember, if it were such as 2x plus 1, you would have to subtract 1 and divide by 2. But our zeros should be -1, +1, and -3. So that's going to really help you to graph this, because you now know the 3 points that it intersects the x-axis. So finding the zeros, we're going to graph the zeros by plotting points on the x-axis. So at -1, put a dot, +1, and -3. Okay, now that's not enough to graph it, because we don't really know how, does it just go up and down, how does it go? So we use our graphing calculator at that point to assist us with sketching the graph from there. So go to your y equals and type in the function as you see it. You do not need to FOIL and get it in standard form, just type it in with the parentheses. And zoom 6 always to restart. And actually zoom 6 is a nice pretty picture this time. Now, because this is a sketch, okay, it does not say it has to be precise and 100% correct. You don't have to calculate the relative max and min using your second trace if you don't want to, because nowhere does it say you have to list them like we did in our homework. Now, if it did, we would perform second trace. But instead, you can actually press the trace button, just trace, not second trace. And that will throw a point onto the curve. And you can now see what that point is underneath. So it goes down to 0, -3. So go plot the point, 0, -3. Let me pick a different color. Did everyone's cursor throw it on the same spot as mine? I don't know. It does, but now you can take that cursor and you can move it around, so you can find approximately what the relative max is without having to do as much button pressing. So it looks like it's about at -2, 3, approximately. So go to -2 up to 3 and put a point. And that's probably enough now to see the upward, downward, and back upward motion to be able to sketch the graph. But if you wanted to, you could pick some other points, but that's really enough. Those are your critical points. Zeros, maxes, and mins. So just take your pencil. Do not connect the dots with line segments. It should be a curve. Right, so it should be round. So just slowly take your pencil and draw it so that it looks somewhat like our graph. Arrows on both ends because it goes up and down forever. All right, example B. Who can give me the 3 zeros that we would find based on the equation? Dylan.
7, 5, 3.
7, 5, and 3. So start by plotting those. They're all on the positive side. And then again, we'll go to our y equals, type in this new equation to find out the maxes and mins. So factored form is really friendly for graphing because you don't have to do as much second trace work. And pressing our graph button or zoom 6. So we can see that it's definitely going up, down, and back up again. We want to have roughly how high it's going and how low, so throw your trace button on there. Press trace. Now notice it jumps to 0, negative 105. Okay, so that's really far down on the y-axis. We're not going to be able to plot that. Okay, but just keep pressing the right arrow until you find it coming up from the bottom. Okay, here it is. It's blinking. Again, if you don't see a blinking cursor or you don't see X and Y, you didn't press trace, single trace. So go up to where the relative max is located to get an approximate point there. Looks like 3.9, 3, which, so maybe that's like 4, 3, approximately. 4, 3. And it can be approximate this time. And then travel down to your relative min, which looks like 6, negative 3. And then just take and draw a curve going through those points. All right. Now below we're going to use what's called the factor theorem. We're basically going to work in reverse. So what the example is going to give you is it's going to give you the 3 zeros. It's going to want you to work backwards to give me the equation. Okay? But they're going to want you to put it in standard form, which means we're going to have to FOIL a bunch of stuff as well as we did yesterday. So the factor theorem just basically says that if x minus a is a linear factor, if and only if the value of a is a 0. So for example, if x minus 2 is a linear factor, then x equals 2 has to be a 0. We know that. We set that equal to 0. They ask us to write a polynomial function in standard form, okay, which is not factored form, unfortunately, with the given zeros. So the first thing you want to do is write out each of these zeros as an x equals. So this is really x equals 2, x equals negative 3, and x equals 0. After this example, you probably won't have to do this step again. But just so you understand how we're going to get to the next part. So we're going to go from giving the 0 back to the linear factor. So we're going to use inverse operations to get it back to be x minus 2 equals 0. We'll use inverse operations to add 3 to get x plus 3 equals 0. And x equals 0, if you subtract 0 or add 0, it's still just x equals 0. Doesn't really change anything. It's not a number. You can subtract or add it, get the same thing. So now we're going to take all 3 of these linear factors and we're going to write them together in one equation. And it needs to be a function or an equation. So we need a y equals, just like up at the top, all of our examples are y equals whatever. And we'll have x minus 2 times x minus, or excuse me, plus 3 times x. That is now in factored form. Unfortunately, they want it in standard form. So how will I multiply these things together? A couple different ways to do it. What do you suggest? Aiden?
FOIL it and then distribute the x.
Sure. You can FOIL first, then distribute the x, or you can distribute the x to one of the binomials only and then FOIL. So we'll get x squared plus 3x minus 2x, which would be plus 1x minus 6. And then distribute your x through. And always just do a quick check at the end. The equation is a cubic function, and it should have 3 zeros. So it should be cubic. So if you ever do this and you get a quadratic or a quartic, you do something wrong. If you really wanted to check this, you could graph this in your y equals and look to make sure that those are indeed the zeros where it crosses the x-axis. Okay. Example B is a little bit harder because none of them are 0. We have 3 distinct integers this time. So again, these are your x equals, which you can save time by just writing them there. So we're going to use inverse operations to get the linear factor. So if x equals negative 4, the linear factor should be x plus 4. Negative 2, add 2 to both sides, we should have x plus 2. And x equals 1, subtract 1 from both sides, x minus 1. Okay, this is just like what we did on our notes, the past two notes that we completed. You need to FOIL 2 of them. Again, my suggestion is to FOIL the second 2. But you can do the first 2 if you want. But I saw some of you on your homework still not getting this because you only have one line of work, and it's impossible to do in one line of work. FOIL first, your first set, x squared, minus 1x plus 2x would be plus 1x, and minus 2. Then you need to distribute a bunch of times. Take the x, distribute it to all 3 terms. Take the 4, positive 4, distribute it to all 3 terms. And then just collect your like terms. And do it in descending exponent order. So bring your x cubed first. We have 1x squared plus 4x squared, which will be 5x squared. Negative 2x plus 4x plus 2x. And minus 8. Again, double check that it's cubic. Therefore, we should have 3 zeros. And if you got time on your test, you would want to click on your y equals button and check that it goes through at negative 4, negative 2, 1. Now on the back, we're going to see instances where you may get the same 0 twice. And that's going to be called a multiple 0. Okay, so we have a little example up here given to us. Using our graphing calculator, find the zeros and sketch the graph. So I want you guys to do that really quickly. Find the zeros and sketch the graph using your graphing calculator. Then so it goes up. Oh, I didn't do that very well. Oh, I plotted, it should be negative 5. There we go, that's right. Negative 1 and negative 1. Okay. So it goes up really high, off your grid probably, comes down, hits, and then it turns around and goes back up. Okay? So it looks like you only have 2 zeros. But technically you should have 3 because it's a cubic. So notice that the polynomial above has 3 zeros, when we listed them, 1, 2, 3, but only 2 distinct zeros, meaning different. Okay? If a linear factor of a polynomial is repeated, so if you see x plus 1 and x plus 1, then of course the 0 will be repeated. A repeated 0 is called a multiple 0 because it occurs multiple times. And the way that we would write the answers for a multiple 0 is to say that it has a multiplicity equal to the number of times it repeats. So if I asked you for the example above to state the zeros and any multiplicity, you would tell me 5, comma, negative 1, and negative 1 would have a multiplicity of 2, because it occurs 2 times. Okay, if you want to abbreviate multiplicity with M-U-L-T dot, that's fine. But you can't just write parentheses 2, it has to be multiple of 2. Multiplicity of 2. And what that's going to indicate in your graph, if it's a multiple 0, it turns around at that point. It changes direction, which makes it a little bit different than some of the other ones we've seen. So we have 2 examples where they did not give us the graph. They've given us one in standard form and one in factored form. Factored form is going to be the easiest one. Standard form, we have to factor it first. So how do I factor? How do I factor? Greatest common factor, which is x squared. So we're going to divide everything by x squared. Do not get rid of it. Put it out front. Remember, you subtract exponents, so this should be x squared plus 6x plus 8. keep factoring. Multiplies to 8, adds to 6. 2 and 4. And then actually find the zeros. Now the biggest mistake, obviously you guys will get these ones, right? So you'll tell me x equals -2 and x equals -4. But then a bunch of you will not know what to do with the x squared. Remember, x squared is actually x times x. And if you're using the zero product property where you set each thing equal to 0, you should get x equals 0 and x equals 0. Because it's a square. So that would be 0 with a multiplicity of 2. Comma, -2 and -4. So there are questions on your quiz next week where it'll ask you to find the zeros and state any multiplicity. Now there's a chance there's no multiplicity. They could all be distinct zeros. The next one is in factored form. So do not start foiling it. That's going to undo what you want done in this example. But we do see that a linear factor is squared. So that will get expanded to be x plus 1 and x equals 1. And then find all of your zeros and state the multiplicity. So see if you can do that.
Multiplicity of 3 and then
Mults of 3 and what else?
2.
2. Perfect. Again, double check that you should have 4 zeros because you had 1, 2, 3, 4 linear factors. Okay? All right, the equivalent statements about polynomials are just different ways to basically say the same thing. Okay? So we have, filling in the blanks, if the board doesn't crash. -4 is a blank of the following equation. Well, if we were to factor this, what would this factor into? What two linear factors? Good. And then if you were to use your zero product property, you would get 2 of your answers, x equals -4 and x equals 1. So the blank is that -4 is the answer, but I think for math we say the solution is a solution. Solution is the same thing as the answer. That is one of our answers to the equation that it equals 0. Now then they talk about, for part 2, -4 is a blank of the graph. Now notice this now says y equals instead of equals 0. There's 2 words that you could probably fill in here, but we graphed this before, so, or we found the equations. -4, +1. Which type of intercept is that? An x-intercept or a y-intercept? X. So -4 is an x-intercept of the graph. Okay, the next one says -4 is a blank of the same equation. This one we would can call a 0 of the function. So these are all equivalent statements. And then the last one says x plus 4, which was what we factored it into. This is called a linear factor of the polynomial. So all of those are kind of interchangeable whenever you're talking about these types of functions. All right, closure says, how can you determine where the graph of a polynomial function crosses the x-axis? There are multiple answers. We can give me one. So looking back at this example, how did we find out where it crossed the x-axis? What kind of math do we do? Aiden?
Equal the function to 0.
Set the function equal to 0, and then did what?
And then solve for each point to contractor.
What do we do from here to here? What's this called?
Oh,
Unfoiled, which is factoring. On your homework last night, how did you find the zeros? On the back of your homework, how did you find the zeros? Yeah? Graphing calculator. then if it's a quadratic, you could technically still do completing the square, quadratic formula, all that good stuff. So the quadratic formula does come back up here.